So we're told this experiment is it's designed to investigate Newton's second law, which we know is F net equals ma. So David arranged for a heavy trolley. And whenever there's an adjective used, we want to be suspicious that it may be important for us. A heavy trolley to be accelerated by small weights. Small weights, as shown below. Acceleration of the trolley has been recorded electronically. David recorded the acceleration for different weights up to a maximum of 3 newtons. He plotted a graph of his results. Drawing free body diagrams right now will be helpful to us. Should be helpful to us. Force of gravity, force normal, equal and opposite. There is a tension. Let's call that T1. On this side, we have Fg, and we'll call it Fg2, call that Fg1, and we have a T2, like so. It's on wheels, so it's not something we should be concerned about with friction, and there's no mention of friction. So we are told in the AP, unless we're told otherwise, to assume it's frictionless. We're now asked to describe a graph that would be expected if two quantities are proportional to one another. If two quantities, well, if any two quantities are proportional to each other, it should be a straight line graph that passes through the origin. We're asked to describe the graph. So the graph should be a straight line that passes through the origin, and we could just say that clearly. We can see there's 2 points, so straight line through the origin. Straight line is about the constant slope. And the origin means that the y-intercept is 0. And I like to add those parenthetically in each of those cases. The next question, here's data's David with uncertainty limits included for the value. Draw the best fit line through these data. So we can certainly do the best fit line. And we can kind of slide that along and ask ourselves which one's the best. So there I've got 3 points directly on, 1 off and the other one off. And so that's probably about the best I'm going to get right there. And again, we want to draw it off both edges of the graph so we have the largest straight line possible. Now what we're going to do, before we get distracted, is to do our Oizerga. The origin we see is 0, 0. The y-axis is acceleration in meters per second squared. The x-axis is weight in newtons. The intercept in this case, there is an x-intercept, and that x-intercept occurs at about right there, which if we see there are 10 spaces in 0.5, that goes by 0.05, so that's 0.1, 0.2, 0.3, 0.4. So we have maybe 2.8, 0.28. So that's at about 0.28. We can read acceleration. We can read acceleration and weight. The gradient is delta y over delta x, so it's the acceleration over the weight, which is a force, and lo and behold, we've got F and A. Well, Newton's second law is F equals ma, and to get A over F, we would divide both sides by F, and we'd have to also divide both sides by m, so we are left with 1 over m. So the slope is 1 over the mass. The area would be acceleration times force, which is, since force is ma, so that's acceleration times ma, so ma squared, whatever that might mean. Well, now we've done our due diligence. Explain what is meant by systematic error. Well, systematic error, the definition of it, which we need to know, is an error that affects all values or measurements, data, the same amount and in the same direction. An example would be an electronic balance not zeroed that reads negative 0.48 grams before objects are placed on it, are placed upon it. All masses will be recorded as less, same direction, by the same amount, 0.48 grams. So that's what's meant by systematic error. Now we are asked to estimate the value of the frictional force that is acting on the trolley. Well, wait a moment. We said something about no frictional force mentioned before. Well, it says there is a frictional force. Let's go back to our setup and analyze what's going on here. If there is no friction and we put even the most tiny mass on this, tiny weight on this, the cart and the mass system will accelerate. And so all that will happen is we add more and more weight, the system will accelerate more quickly. But what this says is when the weight is 0, there's no acceleration. We have to add 0.28 newtons of weight before it accelerates. So it's only at that time that there's enough weight to equal and overcome the friction. So we are going to say 0.28 newtons. Now let's do a sidebar here. Again, I can't emphasize enough how important oizerga is ahead of time because it draws our attention to all of these things before we're asked the question. Now we're asked to estimate the mass of the